Hello, my name is Luke Meyers. I am going to talk a little bit about monoids, the good stuff it brings along, and a bit about how it can help us software devs in our software engineering endeavors. This presentation could be called semi-groups in software engineering, and keeping the content the same, everything would still hold true. This is mainly because I don't talk about the identity element, something that makes a monoid as much as I should. Just for reference, a monoid is a semigroup with an identity element, or you could say that a semigroup is a monoid minus the identity element. I like Haskell a lot, and as a consequence of that, this presentation has a bunch of Haskell in it. Not too much, but just enough to know that this will probably stick out a bit in a Clojure conference. But please do bear with me. The origins of monoids. This abstract algebraic structure comes from the field of abstract algebra. Abstract algebra is the same field that studies other abstract algebraic structures like groups, rings, and cool stuff like vector spaces. In terms of the generalness hierarchy, a monoid falls between a semigroup and a group. A monoid is less general than a semigroup, but more general than a group. The mathematical definition of a monoid. More than often, people mistake the set that a monoid is defined on as the monoid itself, which is false. A monoid is always a triplet. The set forms the first part of it, the binary associative operation and the identity element forms the other two parts. So a monoid is a triplet of those three things. The laws that a monoid must obey. This could very well be the laws that they obey as a consequence of being a monoid. So the first law, or the first item on that list, just states that the binary operation that comes along with a monoid is closed under the set that the monoid is defined on. That means that if the binary operator takes in two elements from the monoidal set as its operands, the output will be another. It could be any element from the monoidal set. The second item states that there exists an identity element for the binary operation that forms a part of the monoid. And the third one, and the most important one, is that the binary operation is associative in nature. So, the first example of a monoid, and I think there are three examples that I'm about to give you. The first example is a pretty trivial one. The set is a set of all integers. The binary operation is the integer addition one. It's not too hard to see that it's associative in nature, and 0 is the identity element for integer addition. So the three form the monoid. The first example of the monoid, of a monoid. I'm sorry. The second example is the same set of. The set is the same as the one before, is a set of all integers, but the binary operation here is multiplication. It's not too hard again to see that multiplication is associative in nature, and 1 here is the identity element. At least the identity element for multiplication is 1. So the set of all integers with multiplication as the binary operator forms my second example for a monoid. And the third example is where the set is a set of all strings. The string concatenation operator is the binary associative operator here, and the empty string is the identity element. It is not hard to see the monoidal laws being followed for this particular monoid instance. So the good stuff that Monoids offers as programmers, I'm going to talk about two of them. The first one being incremental aggregation, and the second one, the declarative interface that the Monoids bring. Incremental aggregation. So, Monoids are known for their part in parallel processing. They're known to use their associativity for breaking down computation into parallel chunks. But even if you don't use this concept, the associativity aids in something called incremental aggregation. I thought it was best to explain the concept by using two examples. The first example where the concept is possible because of associativity, and a second example where the concept is not possible because the operation is non-associative. Or the operation I'm going to use for the second example is non-associative. So the first example, we have two computations, computation 1 and computation 2. Computation 1 where add numbers from 1 all the way to 100, and computation 2 where add numbers from 100 to 200, and and then I have the combined computation where I add all numbers from between 1 to 200. Basically the addition of computation 1 and computation 2. So the idea was to see whether or not the sum of lists, whether computation 1 plus computation 2 would be the same as the combined computation. In this case, it is true. It is trivially true. It is trivial because the operation that we're using here, the addition operation, is associative in nature. So again, I cannot emphasize this enough. It is true and trivial because the operation is associative in nature. Now we look at an example where the operation isn't associative in nature. So the operation to consider here is subtraction, and subtraction is not associative. So we have two computations here, computation 1 and computation 2. It's pretty much the same thing as the computations before, but instead of the addition operator, we swap in the subtraction operator. And we do want to see whether or not computation 1 minus computation 2 is the same thing as a combined computation. And it is not the same. Because the operator here is not associative in nature, we cannot chunk it in. The results depend on how you chunk the operation. When an operator is associative in nature, the way you chunk the operation doesn't really matter. But when it's non-associative in nature, the result depends on how you chunk the operation. And which brings us to the concept of incremental aggregation that's brought about by associativity. Associativity enables the possibility of combining more input to an existing calculation without the need for recalculating. So the question is, where would you use such a thing? It's a nice thing to have, but where would you use it? So this is a small case study that I present. This is so the HLearn machine learning library is a machine learning library written in Haskell. Everything from ground up is written in Haskell, using various structures like categories from monoids to monads. So in this library, under some assumptions, Gaussian distributions along with a binary operator that combines Gaussian distributions are framed as monoids. So exploiting associativity, Gaussian distributions for various samples can be combined without the need for combining all the samples and reperforming like prior calculation. So this use of incremental aggregation saves us from what would otherwise be an expensive recalculation. On a small side note, the author goes on to make the monoid a group by adding in an inverse, and by doing so, in addition to being able to add more input, you can take out input from your result without having to recalculate everything after taking off input. So that is a cool example of turning something into an online algorithm, an online way of updating a Gaussian distribution. So the declarative interface. I believe that an abstraction that has a declarative interface enables us to write more expressive code. And to show you that, I have a toy problem that to solve that will make use of such a thing, or rather the solution to this toy problem will make use of such a thing. There is a bit of Haskell in this, and I will go through it. But for now, I don't think you necessarily have to worry too much about the exact details of things. So here, so I have a data type declared that has three fields: a name, an index 1, and index 2. Name, the type of name is string, the type of index 1 is integer, and the type of index 2 is integer. So DB row list is a list of various instances of DB row type. So the problem here, or your job here is, or our job here, is to sort them first by length of name, of the name field, and then by index 1, and then by index 2. And your code is supposed to be modular. When I say modular, I mean that in the future, if I add in more attributes to DB row, to the DB row type, the code is supposed to handle that effortlessly. So this is where I dive in a little bit into a Haskell tutorial. So the data record declaration is just a way of declaring a type, a complex type, or a composite type, rather than a complex type. It's a composite type, yes. So this composite type has three fields: name, index 1, and index 2. To make an instance of this type, you put in what is called the value constructor, which is the thing to the right side of the equal sign, which is, in this case, is DB row. That's a value constructor, and then you put in the values for those various fields, in this case, and in the order that they were declared. So Newton would map to the name attribute, 4 would be the value to the index 1 attribute, and 5 would be the value to the index 2 attribute. So along with declaring your data record, or along with your data record declaration, Haskell gives you access of functions for free. Before stepping into access of functions, so in Haskell, it is a good habit to declare what is called a typed signature of function. So if you go through API docs or whatnot, every function is accompanied by what is called a typed signature. So a type signature of a function is an insight into what the inputs and the outputs of the function looks like at the type level. So these access of functions that I've put in comments, once those are automatically given to you. And name takes, so the the whole colon, the stuff that follows is a type signature. So name takes in a value of type DB row and spits out an output of type string. Same thing for index 1, where it takes in a DB row and spits out a value of integer. So name, so if you go past the comments, if you look past the comments, you see name A. In this case, it'll give you back Newton. Index 1. So these are functions. So access of functions, these are functions. So name is a function. Index 1 is a function. Index 2 is a function. It just gives in. These are examples to show you that you're given access of functions, and it does what it's supposed to do, which is access attributes of instances of the composite data type that you declared. To solve our toy problem, we'll be making use of two functions, sort by and comparing. Here here I've written down the type signatures along with the functions. Sort by takes in, so sort by looks a lot like the sort by we have in Clojure, where it takes in a comparison function and a list of values and gives back out a list of values, which is what the type signature here says. The thing enclosed within parentheses is just a function, which is a type signature for a function that states that it takes in two values of type A and gives back something that is of type ordering, which I'll talk about ordering in the slide after the next one. And it takes in a list of the same type A that's defined in the function, and gives back a list of type A. Again, it's very important to note that the thing within the parenthesis is a function. So it takes in a function, a comparison function, a list of values, and gives out a list of values. So comparing. Now comparing is very interesting because this is what it does. It says that it requires a function, and it'll give back. So we use comparing to take in a function and give back a function, a comparison function that we will use as an input to sort by. So all it says that is to put in a function that transforms whatever it is that you think you want to compare into something that is comparable. That's into something that can be ordered. This might sound strange because for the most part we always assume that there's a natural order to every type that we come across. Integers have a natural order to them, but in some cases, like say like in the story example, db row doesn't have a natural order to it. So in this case we're going to use comparing to give out a comparison function that makes it possible to order db row. So all it does is it takes in a function that transforms something that doesn't have an order to something that does have an order, and gives out a comparison function that does that. So this is an example that uses both sort by and comparing, just to give you a feel of how what using it feels like or looks like. So I've broken down the computations. You don't really have to do this. For the first part, I have f as a function. So I've used comparing, and I've used. So the idea here is that I want to the list. So the idea here is to use the list, is to order the list at the very end by string length. So for that, I first use a comparing function to give me a comparison function that I will use in sort by to sort the list. So f here is that comparison function. So comparing takes length, and length transforms each string into something that into an integer in this case, and because there is a natural order to an integer, that will be how I compare every string in that list. And g is just simply saying that I want to sort. So g is just a shorthand for the function sort by using the comparison function that I defined above. And then g, and so the one thing to note about Haskell is that white space denotes function invocation rather than parentheses in Clojure, rather than use. So g space the list is pretty much an invocation call for sort by f and then the list. I did tell you that I was going to define what the ordering type was and the values for it, and this is the definition. Data ordering is a type, and ordering is a type, and LT, EQ, and GT are the various values that the ordering type can take. So here's where things get interesting. Ordering happens to be a monoid. It has a binary associative operation defined on it. There's no real name to it, but it exists. And EQ equal. So LT is lesser than, EQ is equal, and GT is greater than. So EQ equal is the identity element for the ordering monoid. And the computation below evaluates to true because that operation is associative. So now we go back to our toy problem, and again I've broken down the computations just to be more specific and clear. So using comparing, and various accessor functions, I've defined like three different comparison functions. The first one compares two DB row values by the length of the name. This G is a comparison function that compares two DB row values by the values in their index 1 attribute, and H is another comparison function that takes in two DB row values and compares those two using the values in the index 2. And again, all these functions shoot out an ordering value. So ordering, again, remember that ordering is a monoid. So the values it shoots out are monoids themselves. So the question is, how do I combine all of them into one comparison function, which is the goal for this toy problem? So this is what I could do. I could define an anonymous function that takes in two DB row values, gives it to each one of these comparison functions, have them spit out an ordering value, and because the ordering values are monoidal in nature, I can combine them monoidally. And this works fine, and it's completely fine. And Z would be that whole comparison function, the whole composite function. However, and this is the best part of the monoid having a declarative interface. Once you know something's a monoid, you get a bunch of free guarantees, and one of those free guarantees is this. It turns out that functions that output monoids are monoids themselves. So instead of us defining an anonymous function that goes and evaluates like the inputs against these comparison functions and combines them monoidally, I can just simply combine the functions that spit out monoidal values monoidally. So Z becomes F, monoidal operation G, monoidal operation H. And so in its unaliased form, it looks like the one above. So I've kicked out all the aliasing because it makes it so much more easier. And the end solution looks like the third line. And in my opinion, that is a beautiful solution. It is pretty. It tells you what it's doing. There's no. It's very clean, and yeah. And I find that insanely beautiful. So in the future, if more attributes are added to DB row, like index 3, index 4, all I have to do is just add in more lines like that, and that is my solution. That solution works so well. It is, again, using the declarative interface, we now have a very pretty solution, an elegant solution. It tells you what it does. It concentrates more on the why versus the how, and yeah. So my final notes on this is the monoid is not just another interface with a fancy name. There's a lot more to it. Like once you define a monoid, there are a bunch of guarantees that you get with it. And recognition of what acts as a monoid under certain operations leads to availability of a lot of free guarantees that will lead to better code. There is this one last topic I do want to touch upon, because there is a small little case study that was brought about while talking about monoid homomorphisms, and I think knowing what homomorphisms are will give you a little background and make the case study all the more understandable. So a homomorphism between two monoids is a function that maps. It's all in all, it's a function that maps one monoid to another, such that in a way that it maps the identity element for the first monoid to the identity element of the second monoid, and it maps the result of the monoidal combination of two elements in the first monoid to, or rather, the function maps the monoidal operation of. It maps the monoidal combination of two elements in the monoid set to, or it states that it's equivalent to whatever it maps to is equivalent to the second monoidal combination of the mapped values. So in this case, so an example of that would be the string length function. So the first monoid is a set of all strings, and where the string concatenation operator forms the first monoid, and the second monoid n is a set of all integers, and the monoidal associative binary operation is the addition operator, and so f maps it. So f is the monoidal homomorphism in this case. I'm sorry, the string length function is the monoidal homomorphism in this case. So this is a small case study. Someone came across the following in the Google while doing something, or while reading through the Google protocol buffers API documentation. This is C++ code. They realized that this was a monoid homomorphism in the wild, under some assumptions. They recognized that, this is this. So you have string, that is a string under the concatenation operator as a monoid, and message under its own under its own merge operation as a monoid, and it follows the same monoid homomorphism rules. And so in this case, if merge from this, which is the second monoid's binary associative operator, if that were expensive, it would just be as correct to merge the strings before passing them as it would be to merge the past results. That small recognition would lead to what I think is a pretty nifty refactoring. So, in my opinion, software engineering boils down to three things: domain modeling and modeling transformation of information flow within the domain space / information flow within the domain space, and the last one being controlling complexity. I do want to talk a bit more about controlling complexity. I think it's pretty straightforward to see why beyond monoids, why mathematical structures would aid in the first two. But I do want to talk about controlling complexity, why mathematical structures. So code bases grow complex as time progresses, and I've seen that happen a lot. Subjective intuition doesn't scale, especially not as a code base. It doesn't scale, especially not as a code-based foundation. In cases that it does, I feel it was more mathematical intuition masquerading as something less. In my opinion, things expressed as an algebra of things are more manageable because they're easy to reason about. Monoids are definitely one of those tools that makes it easy to express ideas as an algebra of things. And it's not just monoids. It goes beyond that. It's just the use of mathematical structures as the foundation of how we code. That mathematical structures are such a big ally in our quest to make better software and to control complexity that comes with making good software. These are my references, and yeah, that's pretty much it. Thank you for listening.